Right, so this is basically a demo for our OOP project. Basically, what we've created is a society simulator, and the way it sort of works is it generates a map and it places agents on the map, and then those agents interact with the world and around them, with the environment, and with each other a little bit, and we just see how that society grows and dies across various different changes. But let's just see a demo run of a program. So the way you launch it was we do /main and we pass in a number. So passing in 123 here, and that's basically a seed that's being used to generate the map. So when I put in 123, this map was generated and the players were spread out in a certain way. The green represents grass, the gray is like mountains, no one can go there, and then the blue is water, and the agents can't go in the water as well, else they drown, right? So this is the map that was generated with 123. And one thing we just want to test is, okay, what if I provide a different seeds? Let's provide 3, 4, 5, and we see that we get another map. And if we compare it to our original, we do see that there is a difference, right? So these maps are being procedurally generated based off the given seed. Now, if we sort of zoom in to a specific part of the map and we actually let our simulation run, we see that these agents are sort of navigating towards the green stuff, and that green stuff is actually vegetation and food, and we see that this vegetation and food sort of decreases over time as the agents sort of walk over it because that vegetation is being consumed. We also see that after that vegetation is kind of taken away, these agents sort of try to stick close to one another. It's a sort of survival instinct that we've encoded in. So basically, each agent has a sort of kernel or a matrix which it uses to evaluate the area around it, the area it can see, and it bases that calculation on the vegetation in that local area and the number of people. And so it tries to go for places where it is likelier to survive, so more vegetation or more people. Generally, there are also some outliers which will actually try to go away from population. That's because each agent actually has their own personality. And so there's a lot of these little details that we coded in. But now let's have a more higher level overview of what's going on in the simulation. So we see that initially there's a lot of green land and that vegetation sort of shrinks because people consume it, but also because there's famines. There's certain seasons where the food will just rot and decay. Then we have the season of flooding where the water just expands outward, and this can cause some deaths. And that flooding season is followed by a season of harvest where a lot of food is growing up, and then that is followed by drought, and then that drought causes a famine, which is characterized by the vegetation reducing, and then the cycle continues, and we have flooding again, and so on. So there's this sort of cycle of seasons that control how our environment changes overall, and the way our environment changes also controls how how the society develops. So now if we change a value in our command line arguments to be 1, we'll see that when we start the simulation, we also get this graph. And this is a graph of the number of people that are currently alive. We see that initially it's really high, and then it decreases to 60, 70, and it sort of stays stable around there. That's because each map has a sort of implicit carrying capacity to it based on the amount of vegetation there is and like how fertile the land is. This isn't something we code in, it's sort of randomly generated. Like the land is randomly generated, and then how many people it supports based is just determined off of that on its own, based off how fertile the land is. Right, and we'll see that there will be fluctuations. Sometimes there will be dip, like in the season 25, but then over time, the population size will return to that normal, to that average, which is its like carrying capacity, and in this case, it's like 60 or 70, and this will sort of vary across maps. So if we try a new seed, now we're trying 1024, so it's the seed directly after in a sense, we see that, okay, this has a lot more land and a lot more fertile land. There's very little water, it's very off to the sides, so not many causes of flooding that will kill people. And we see that this land seems to generally have a higher average, like around 100. And yes, there will be dips, but there will be also a lot of recovery. And This land therefore just has a generally higher carrying capacity. Again, there will be fluctuations, but it will return to a normal 100 for this land. And so this was a very interesting result of this simulation. If we now turn to the UML for a simulation, there's a lot going on, but if we sort of zoom in to, for example, the random walker and to the builder, these are basically what procedurally generate our land and populate it with different features and terrains and agents. Now these terrains and agents and features are like stored in a grid which says, okay, which position has what, and the terrain and the features and the agents, they themselves have their own attributes. So for example, if we now look at terrain, it has like whether it's walkable, and it has a step, it has a consume, it has a grow back. So these are different functionalities of terrain, and features are a bit similar. Then we can also talk about agents. Now agents is a very different class. Agents has a lot of different features. It has its name, age, stats. Now, if we look at stats, it's the agent's age, health, wealth, and happiness, and this sort of determines, whether to live or die, but also some of its actions. Moreover, we also have a functionality to keep track of the agent's relationships and their traits, and their traits sort of and the traits are based on Ocean, which is openness, conscientiousness, extrovertedness, agreeableness, and neuroticism. And these traits sort of determine their relationships. That if I'm very neurotic, I'll not have particularly positive relationships. But I might also, but it also affects my relationships in the sense that I might have good relationships with people that are more like me or people that are more compatible to me. And then we also have this interaction manager here, which has a bunch of different social interactions that can take place. Talk, insult, work, hurt, party, reproduce. There's a bunch of these. Although, disclaimer, not all of them are actually being used in the final version of the program. These are actually from our initial idea of using a simulation to see, how society works at an interpersonal level. So our program in its final stage focuses a lot on how the users interact with the environment, but initially we did try to have a focus on how they interact with each other. And so if you look at that, the result of that is that we got some promising results where different relationships would form and different uh, and they develop differently over time. Um, but we realized that this would be harder to model for larger and larger population sizes. And if there were too many different interactions going on, and they were affecting how people were moving and whatnot, it would be a bit hard to figure out what was causing what effect. And so it wouldn't be as clear as to what's going on. In fact, putting in all of that functionality, making it all so systemized, would have made it harder to track any specific change and would actually make it look a lot more chaotic. So that's why we settled on just having a few key features being implemented to just affect how our agents function. But overall, this was quite a fun, quite a challenging, and quite a insightful project. It got me to use Linux, which was a blessing and a somewhat of a curse, but I'm really glad for it. And yeah, I'm very grateful to my teammate Hamad Asif Khan for contributing greatly to this project. And for more, you can always check out our repository on CodeBrick, which is linked in the description below. Thank you.